feels okay, except when I sit for too long, then it just is very painful when I first get up. But then after I move around some, it feels fine. I don't know what it is. Okay. But we are now recording, and let's go from current slide. And before I go any further on this, and this is one of the main things I wanted to talk about, I've been asking my classes if they had opened student course evaluations yet. And some of the students were saying, yes, we've done them. Others say, no, it hasn't been opened yet. I thought, what is going on here? And then they say, well, some students got the email and some students didn't. What is going on here? So finally this morning I asked a student, I said, what was I was actually telling one, look under student course evaluation, surveys, any of those things, and type nothing. And then one of them said, it was in that email that had to do with Student Government Association. What? And sure enough, that's where it was, when it was telling the students to vote for the officers in the student course government. And by the way, the student course evaluations are open, but it wasn't, anywhere else it wasn't in the title or anywhere else. So, do any of you check your Lawson State email? Probably not, right? Okay. If you do check your email, then look for that Student Government Association or some sort of thing on the voting for it. It was like 2 weeks ago or so. So go back at least that far. Now, if you don't even know how to log into your email or something, let me tell you where to go that you can get to it. See, if you go to the email, there's a link. Click on that and you're there. And it's so easy. But if you don't or can't get to your email, hey, and we got 100% attendance. That's great to see. But if you don't check your Lawson State email, here's where you have to go. Talk about student course evaluations. Okay, have you seen anything about them yet? So I don't think anyone in this class checks the Lawson State email. And you probably weren't at all interested in Student Government Association voting. But here's what you do. Go to Lawson State web page, okay? The main web page. And at the top of the page, there's a whole list of blue tabs. Student suite, faculty suite, or employee suite. There's just a whole directory. There's just a whole bunch of tabs up there. They're all blue. And then over near the right-hand side, okay, is a big gold one that says Quick Links, okay? It looks yellow, but we're blue and gold, so it's gold, okay? Click on Quick Links, okay? Now that's going to open a huge menu, okay? Scroll down in the menu until you find something, I believe it's referred to, it's been a long time since I've looked at it, believe it refers to it as surveys. So scroll down till you see the surveys and then click on that and you should see something that says student course evaluations. But if you don't see that, the title of the package, the program, is Smart Evals. S-M-A-R-T, Smart, E-V-A-L-S, Smart Evals. Go to that, enter, it tells you what to enter. It's your student ID number, I believe, and your birth date or something like that. But it tells you exactly what to enter. When you do that, then you will come up the student course evaluations. Is this the only class you're taking here at Lawson? Yes? Okay. If it is, then that will be the only class. However, they may put in another survey or two of things like facilities, landscape, bookstore, cafeteria, some of the other things, registration process. You could be asked to do one other, and maybe even two others. I don't think they would do that, but one or two others. But please do the student course evaluation, any other evaluations they ask. We value those because sometimes that's the best, like, let's say it's the registration process. Who else is going to ask you your opinion on that? This survey will be it. And if you have a pretty strong opinion, then that will get read and understood. And if you don't say it, maybe they'll never hear it, and they need to hear it. We need to hear it. So, please try to do the student course evaluation. You really have till the end of the term, but I remember when I was an undergraduate, and when the end of the term came, basically I turned the brain off and wanted to get home, you know. So don't turn the brain off before you do your student course evaluation. Please do those. So therefore, it might be a better idea to go on and do it now while you're thinking of it. Okay. Okay, and let's also talk about this. We should finish chapter 17 today, and I did not have a chance to come up with a test for it because I think we will come close enough to finishing, but I'll try to have that ready for you on Wednesday. We'll go on into 18, and 18, I think, is just a couple of sections, 3 sections there, and then we'll do as much as we can on 19. But you see, we have class today, we have it Wednesday, and we have it next Monday. Monday, I'll be giving you your last test. It's not going to be a comprehensive final, just the last chapter test will be the final. I will have that one ready for you. Now, here is a possible problem. How do you get those back to me? And I'll find out the details on this by Wednesday's class, hopefully. But I have been designated with a group of others, there's a group of us, going down to Tallahassee one day next week. And it's actually 2 days. We go down, spend the night, and come back the next day. Right in the middle of finals week. And I don't know what days those are, but it could easily be Wednesday. I hope it's not Monday, because that's our last class. But I hope it's, you know, it could be Wednesday. If it is Wednesday, then how am I going to get your tests from you? You can either email them to me, scan them and email them to me, or leave them with the secretary here. Now, she's usually in here when we come in, but leaves pretty soon. Today, she wasn't here at all. This is first day, maybe second day that she hasn't been there, but someone's always been there. Today, nobody was there. So what we, you know, if she's here, you could just come and leave them with her and I'll pick them up. Or, do any of you know the West Campus? You do? Okay. You know there's a quad in the middle of the sort of a circular drive. And in that quad, there's the A building sits like this, the B building like this, the C building like this, and the D building like that. D building's the library, the A building's the administration building. The B building is that long one that goes all across the back. And the end this way is toward the ACAT building and the Student Center, Leon Kennedy Center. If you go in that door, you go down that long hallway on the B building till you get to just before you go down the stairs on the other end. If you come in the other end, as soon as you walk up that half flight of stairs, it's the door right at the left. It's my office. You'll see it on on the syllabus and stuff. B112, okay? And you can take it and drop it by there. Usually the secretary's there at least before 5. So if you can, if that's inconvenient to you, you know, we'll work something out. We'll talk about it next week, you know, Wednesday and next week, and we'll come up with a way to get those tests back to me.
Is it possible for you just to post them all up there?
Say again?
Is it possible for you to post all the tests up there and then we can just turn it into you on our last class?
Oh, okay. You mean do it before we have the last class?
Just have them all up there. We can work on it, and people who don't have an opportunity to get it to you by our last class.
Right. Well, the thing is, I don't know how far we're going. Well, yeah, I got to have it made out anyway. I can try that. Yeah. Put it there, and that's worked okay in the past for everybody when I put them on Blackboard. Okay. So yeah, I'll try to do that that day. But I put them there, but how are you going to get them back to me is what I'm asking.
Well, we'll see you on that Monday, correct?
Oh, I don't, okay. Oh, you mean like,
Do
yeah.
it this weekend and bring it to you on Monday.
Okay, well that means that means I have to
You have to have the test made.
Before the class on Monday, and all of you will come for class, won't you? Yeah, we'll try it that way if I can, but that means I have to have the last 3 tests made out and given to you by Wednesday. You know.
That is a lot. But he's going to give it to you anyway.
What's that?
You're going to have them anyway.
Yeah. Yeah. I'll have this test and probably 18 done Wednesday. I just wasn't planning to do 19 as well, but I can. But we'll see. Huh? Oh, y'all are kind, aren't you? You are just so good to me. Yeah. All right, let's see where we can go on it anyway. Okay. But I'll find out when the trip is and all that kind of stuff and what we can do. If nothing else, you can come here and leave it on the table here. I'll check with the secretary and see if she'll leave a folder here that says PHY112, work or something like that. You can slide it in there and I will come pick it up then whenever I get back in town. So that might be easiest. Hope it'll be fairly secure here. But I'll check with the secretary and see. Okay? Any other questions? Okay? Sorry about all the uncertainty at the end. I can't imagine what the rationale was sending a bunch of us, where most of us instructors, out of town during finals week. It's nuts. It's totally crazy. And, of course, it was done by the administrators who, they don't teach classes and they don't think about, oh, it's important to be there during finals. They don't, well, I'll shut up. I'm recording it. Okay. All right.
You have to restart the recording.
Yes. Not that they'll ever listen to it. Okay. Okay. My mark was, any questions on anything? Yes. Oh, yeah, your question. I'm sorry.
Page 324.
Okay.
Page 324.
Test number 4?
Page 324.
I can't hear. Okay. 344.
324.
324.
Yeah.
I really can't hear. Page 324. Got it.
Number 8.
Number 8.
8 and 9.
Okay. And I meant to say this too. I've already complained about how lousy the PowerPoints are here. Their test bank is not much better. I think I've told you on several of the tests, I'll be grading them and say, why are all the people missing this, And then I'll go back and work through it and find out the test bank was wrong. The problem was wrong. Something was wrong in it. On the test that y'all are working on now, or the last one that were turned in, question number 1, first 2 tests, got the same answers, not the same one. I went and checked. Their answer was wrong. The next question, no, a little bit further down the thing, the question is stupid. Okay? Let me see if I can find it. Yeah. And I think this is the one referring to yours. If you see this number 3 on this test, is that what you're referring to? The vertical steel columns of an office building each support a weight of 50,00 pounds. What's that? It's supposed to be 50,000 pounds. Okay? But the first 2 people that turned it in, or at least one of them, worked it as if it was 5,000 pounds, which would have been a reasonable thing, only I said, if that's all it's supporting, this is a pretty poor building, okay? So it should be 50,000 pounds. But I counted, if you did the work right based on their lousy number, then I gave you credit for it, okay? So this is one. And then on the B part, what would be the compression if the weight were 60,000 pounds. That's supposed to be 60,000 pounds. But the good news is the B part would be the same answer. If you put them both as 50 and 60,000, then the ratio comes out the same. The A part is one that would be off by a factor of 10. But if you did it based on their numbers, I gave you credit for it. So let's do. Goodness, it hurts to bend my knee. Oh, okay. Let's do page 324. Let me see if I can find. Such a pain in the neck. Okay. This is probably the most white space. We'll do it here. So page 324. Whoops, let me get my pen set up. Okay. Page 324, problem set 12.2, number 8. Each vertical steel column of an office building supports 30,000. This made a little more sense. Here's what I think happened. I'm not certain, but I believe it did. Pounds, and they put a line over that 0. I'm wondering if on the other one they did that kind of stuff and the typesetter thought, oh, maybe I'm not supposed to put that last 0 for some reason. I don't know. And is compressed .00234 inches. Okay? Find the compression of each column. That's dumb. Of each column. Okay? If a weight of 120,000. If weight of 125,000 pounds is supported. Okay. Now, what would be your approach to a problem like that? I know you're asking me, but how would you approach it? I know this isn't quite Hooke's law, but it's really, really similar to it. What do you get from that first set of information they gave you? That's enough information to determine your K, compression constant. And that's usually in newtons per meter, pounds per foot, or something. This will be pounds per inch. So your K, your constant here is 30,000 pounds divided by 0.00234 inches. Now, these aren't the usual units, but you can use any units you want to. Plug that into a calculator, and you'll see it's going to be a big number. Very big number. What do you get it to be? 1 point what?
128.
Oh, 128.
205.
05.
205.
205. Is that right?
Yeah.
Okay. And that would be pounds. Second?
I'm not done yet.
Oh, you're not done yet. Okay. All right. Continue.
1, 2.
Another 1, 2 after the second 205. Okay. 1, 2.
0.82.
Second. Point.
82.
82. Okay. All right. It's a lot of digits. Okay. Okay. That would be 100, thousands, million, 1.3, 1.28 billion. That would be a pretty good guess. Pounds per inch of compression. Okay? Now, most of the time they'll get that in scientific notation. Okay? Now, what we have is that ratio. As long as it's the same column, same material, and you haven't approached your plastic limit or rupture limit, then you'll use that same constant, okay? So you're wanting to know the compression, that's your unknown here, if you have 125,000 pound supported, okay? Well, you take this same formula, okay? This is force, and this is compression, right? And the constant is force per unit compression. So the compression would be constant is equal to force per compression, okay? So if you multiply both sides by compression and divide both sides by your constant, the compressions move out here and you get compression is equal to, and the constant divides out here, force over the constant, okay? Well, you got the force, 125,000 pounds divided by your K, which was that big number. I'm going to write it this way, 1.28 times 10 to the 3,699 pounds per inch compression, okay? The pounds go out, and this is going to give you a fairly small number, but bigger than the one we had before. See what you get there. 125,000, yeah, 125,000 divided by your 1280520.512.80 inches per pound, pounds per inch. Anyone got it yet? Anybody? It's going to be 0.0, and I can't tell. I'm thinking there's a second zero and then a bigger number. What is it?
I got 0.00009.
Whoa. 3 zeros?
No, I have 4 zeros. I did it wrong.
Okay.
He said, whoa.
Yeah.
I'm just telling you.
What's that? Yeah, I'm guessing 2. 0.00975. I knew it was going to be pretty close. Okay. And that would be inches. Okay. I knew it would be pretty close, and that's awfully close. A little bit more and you would have been 0.01 something. So that looks like a reasonable answer. That is an even, so those aren't in the back, are they? I haven't checked them to see, but I don't think they are. Okay. Does that make sense? What's that? You got what?
I got 0.00097.
Oh, wait a minute.
See, it's just everybody's different.
Okay. This is 1.25 times 10 to the 5th divided by...
I just used the big number. I just plugged in the whole big number.
Okay. I haven't checked to see if those units are right. If we divide this by 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. No, I think there's too many numbers there. That's where the error is coming in. I think this is supposed to be 128. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm guessing the decimal should be right there. So that seemed like such a huge number. Okay. So I believe it's 12,000,000.8. I don't know. but just my gut feeling, that's what it would be. I don't have a calculator up here to check on it. I could get mine open, but it's such a pain in the neck.
It's 128. Yeah, that. Yeah, 0 and 5. That shouldn't be in there. It should
What's
be
that?
It should be 128.20512.82.
Okay.
So that 0 and 5 after the 8 should be gone.
Oh, okay. Right. Say it again then. 128
205
205
12.
116
No, you got it.
1282.
Yeah,
Okay.
1.82. Sorry.
0.82. Okay. All right. That's making more sense. I thought it would be in the neighborhood of 12 million. Okay. I didn't know the 05s were in there twice. Okay. And then when you divide that, you'll get the right. Yeah. Good deal. Does that answer your question?
Yeah.
Okay. Any others?
Yeah, number 9.
Number 9 on the same page. If the compression of each steel column in problem A is 0.0279, what weight is supported by each column? Okay, so we've still got the same columns, same constant. So this time they give us the compression is 0.0279, and they are asking for what weight or force is supported by each column. Well, again, let's go back to our original formula here, that compression is equal force divided by, well, we had it several ways. Compression is equal force divided by compression. So this time let's multiply both sides by compression, just like we did before, but don't divide by this, and the force is equal to K times your compression. So the force, or the weight, is equal to the constant times this compression. So that would be 1.28205. Well, how about 1.282? We'll give an extra digit here, times 10 to the 367. Multiply that by, that's your K, your compression, 0.0279. Okay. Well, I just rounded off to keep from writing them all down. 1.282. That's what I got up here. I just rounded at that decimal place. 1.282 times 10 to the 7th, because there's 7 zeros there, or 7 digits there. And then multiply that by 0.0279. And what do you get there? That would be the weight supported by each column. It's going to be pretty much greater than 30,000 pounds. I would say more than 10 times that. Probably 325,000. So,
35.
say again?
35.
35,
76.
76, 7 what?
78.
78. Yeah. Okay. Underestimated. It's more than a magnitude of, power of 10. And that would be pounds. And of course, that many digits don't make a lot of sense. So I would say 3.58 times 10 to the 5th pounds. That's probably how they give their answer. Now that one should be in the back. Let's see if it is. This is chapter 12. This was 12.2. Number 8 was 3.57. They rounded sooner, times 10 to the 5th pounds. Yeah. So that's making sense. Of course, they had to do number 10 to get that. I mean, number 8 to get it, but they didn't give you the answer for 8. All right. Does that answer this one?
I have a
Yeah.
question on the chapter 16 one. Like on question 9. It says,
16, you said, chapter 16?
Yeah.
Okay.
It says a car is traveling away from you at 70.7 miles per hour. The car horn produces a sound at a frequency. Of what frequency do you hear? I think we're missing numbers in 8 and 9. Like, I don't think you can
Okay.
do those questions.
Now, you said chapter 16,
Uh-huh.
but where in chapter 16?
It's on the test. I don't
Oh!
want you to work the problem out. I just want to show you that I think we're missing.
Okay.
Yeah, I don't think we have enough information.
See, I told you, this
See right
test
here.
bank really stinks.
See, it says the car horn produces a sound at what? And then I think we're missing a number for that one too, because it don't tell you what the whistle, the hertz is for how loud the whistle is to get it for the train. So
It just means it's correct. Whatever you put.
that's what I'm saying. Like I don't know. Like,
This is
we can just try a small
this is
page?
absolutely amazing.
Yes.
Belong.
Those are the only two I'm slept on.
I mean, I was like,
All right.
just curious. That's all.
No, good questions. I really hate this this book. I mean, the book's not bad, but their support stinks. Let me find. Okay. See if I can find. Ah, good. Okay. Force out. Okay. Yuck. Okay. All right. See if I can work this out fairly quickly. I don't think I can, but I'll try. Okay. Okay. Yuck. Okay, here it is. Oh, yuck. All right.
Sorry.
Well, it's just, I don't have a calculator here, so
Oh, my calculator?
You can
Huh?
have it.
Okay, if I can bum one for a minute.
You can keep it.
Okay. Thank you. Ah. Oh, okay. Yuck. Okay. Oh, they have all the review problems in the back. Okay. I think I have... Oh yeah, okay, this makes sense. I think that first one, which number was that? Number 8. And sounds a whistle of 585 hertz.
585 hertz.
Yeah. I think that works. Oh, here's, I was looking for the page. Okay. And the second one, oh, there it is. Oh, scratch. A car is traveling away from you at 70 miles per hour. Okay. And I assume on that one we'll use the same speed of sound in air that we did before, 1090. Okay. Let's just say that the car horn produces a sound at 5,000 hertz. Okay? Y'all got it? Okay. Number 9 was 5,000 hertz, and number 8 was, I didn't write it down.
585 hertz.
Huh?
585.
585. Okay, that sounds reasonable.
That's the answer?
No. That's the question.
Oh.
No. You think I did all that work to give you the answer? Okay, number 8.
That was me.
Okay, number 8. A train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle with a frequency of 585. Okay. That's where you put that. It sounds a whistle with a frequency. What frequency will be heard by the observer? Assume the speed of the sound velocity in the air is 1090 feet per second. So number 9 then, a car is traveling away from you at 70 miles per hour. The car horn produces a sound at a frequency of 5,000, didn't I say?
Yes.
Hertz. What frequency do you hear? Okay. Does that handle those for you? Okay, and I get a new calculator to boot, right? Oh. Sorry. No, that's all right. I need to move. Poorly, but moving. Okay. All right. Any others? I apologize for this. I wish I had time to work the problems first and make sure there are no errors, but as it is, usually I'm running like crazy trying to get the thing run off. I just made the stupid assumption they know what they're talking about, and they don't. It's really pathetic. What's that? On page 337? Okay, okay. You said page 337?
Yeah.
Okay, wait just a second. Let me put my marker back in. 337. Okay, 337.
Yeah, number 8.
Number 8. Top of the page, right?
Yeah.
A cylindrical piece of copper is 9 inches tall with and 1.4 inches in radius. How much does it weigh?
Let's assume the inches are in centimeters.
Say that again.
Assume the inches are in centimeters. Instead of saying inches, let's say like centimeters.
Okay. You're saying something about inches. I couldn't understand.
Yeah.
What about it?
I'm saying instead of the inches, let's say that like 9.00 centimeters.
She's saying use centimeters instead of inches.
Okay. Okay, why? I mean,
Yeah, because that's how the problem is on the test. It's not on inches, it's on centimeters, but it's a different problem.
yeah, but I'm not going to work the one on the test for you.
No, I'm saying this is a different problem. It's not the same on the test. So you can watch it if you want.
Okay. But if you know how to do it in inches, you should know how to do it in centimeters, right?
No, I don't know both ways.
What's that?
I don't know. That's what I'm asking.
Well, yeah, I mean, everything should work the same.
Oh, so you don't have like to convert.
No. In fact, I see a lot of you doing that. The problem is given in feet and whatever, and then you're giving me answers in newtons and stuff. I have to go back and check to see if you made your conversions right. If it's given in feet, give me the answers in feet, you know. But I give you credit for it, but there's, you know, is that your issue here, conversion, or is it?
Yeah, because I don't know if it should be in centimeters or
You don't know if what?
if I should convert.
If there's no reason to, don't go back and convert. I mean, use what they gave you. For instance, a cylindrical piece of, let me clear all this out of the way. Okay. A cylindrical piece of copper is 9 inches tall. Okay. Okay. So this is 9.00 inches. Okay. And 1.4 inches in radius. So the radius here, 1.40 inches. Okay? Now mine isn't drawn to scale, so don't even expect that. How much does it weigh? Okay? Now, what would be some of the steps to get the answer? We're looking for the force due, the weight. This is what we're looking for. What does it weigh? What would we need to get that? What physical principle is it dealing with here? If you have your dimensions of a thing, and by the way, it's copper, okay? That's key. What are you needing to do here? Tell me, just the procedure, what you're thinking on it.
Find the area.
Okay, area isn't going to give you very much here. But that you do need to find the area of the base. So let's do this. The area of the base is what? Give me the area of the base. This is, oh, I'm sorry, I forgot to write it down. This is page 337, problem set 12.5, number 8. Page 337, problem set 12.5, number 8. So yes, the area of the base is important. That's either the area down here up top or at the base. It doesn't matter. It's uniform, even though my picture doesn't look like it. What is the formula for the area of the base? Pi r squared. So that's pi times the radius, 1.40 inches squared. Okay? Now, that just gives you the area of the base. What do you really need to work this problem? Okay, what principle is this problem need you to employ? What is it specific about copper that's going to give you the answer to this? Whether you're talking about a copper penny, a copper wire, a copper cylinder, whatever it is, what is true about copper? Always true about copper. Did I hear something? If you turn back a few pages on page 330, you have a table there that I think you might find useful. Say again? Is it what?
She says the mass or the density.
It's the density, yes, exactly. That's what we're going to be using. Because you see, density is what are the units for density? The weight density, the one to the right. Pounds per cubic foot. Okay? Well, the weight density would be the weight divided by, I'm sorry, wait, let me start over there. Okay? See, units are your friends. The density, I'll call it D, weight density, is equal to weight per unit volume. That's what you need. Okay? We're looking for the weight, so multiply both sides by V, and that gives you force due to weight. In other words, the weight is equal to the density, weight density, times the volume. Okay. So, we have in our table there the weight density for copper. What does it say it is? Weight density for copper from the table is 555, but note the units. Pounds per cubic foot. Okay? Here's a problem, Houston. Our dimensions over here are in inches. Okay? So what we're going to need to do is calculate the volume of that cylinder in cubic inches and then convert that to cubic feet. Okay? So the reason I let you go on with that area, you need to know the area of the base to multiply it by the height to get the volume of the cylinder. Right? So your pi times 1.40 inches squared, and then take that and multiply it by 9, so that would give you pi times 9 times 1.40 squared, and that would give you the volume in cubic inches. So figure out what that is. Pi times 9 times 1.4 squared. It's going to be on the order of 1.4 squared is going to be close to 200 or 2. Let's just call it, no, yeah, close to 2. Okay, times 9 will be close to 20, times 3 would be close to 60. Something around 60 cubic inches? I'm guessing. Has someone done that yet? Pi times 9 times 1.4 squared. 65? 55. Okay, that sounds reasonable. 55 point, say again? 3896, and that would be cubic inches. Okay? But we've got this in cubic feet. So what we've got to do is multiply this by a conversion factor that gives you cubic feet. So what units go where? The first blank is for numbers. Leave that alone for now. Put the units in their place. What unit go? Which is? Feet on top, inches on the bottom. Now how many inches in a foot or feet in an inch? 12 inches, 1 foot. Perfect. But we've got cubic inches and cubic feet. Now, I'm going to cube 1. I'll do that one. Y'all cube 12. So take your 55.3896 or whatever you had there, divide it by 12 cubed, which is a very large number. So that's going to make this number of cubic feet pretty small. What you get?
0.032.
0.0 what?
32.
32? Is that it?
07042.
07, blah, blah, blah. Okay. Now, take that number, just like you got it on the screen, and multiply it by the 555 pounds per cubic feet. And that's, multiply it. You see, from up here, the weight is equal to density times volume. Your density is 555 pounds per cubic feet. You just told me that was 0.03207 or something like that cubic feet. So multiply that number on your screen by 555, and that should give you how much the weight is.
17.799.
799. Let's call it 17.8. Okay? 17.8 pounds. And please don't go back and convert that to newtons. I mean, the answer is pounds. Now that answer is, this is review exercises, so that should be in the back. 12.5. Okay. Oh, no, this is problem set 12.5. It won't be in the back. Sorry. Well, nope, it's not. Sorry about that. I was thinking that was review exercise, but it wasn't. All right. Does that answer your question? Okay. Any others? You see what's going on? Sorry that the screen is sort of messy. They've got so much writing on it, and then I don't write very neatly either. So, let's end that. And I think where we are in the text, we were doing example 1 on page 469? Yeah, 469. Find the total resistance of a circuit shown here. Okay, let's see if we can get a circuit that looks like that. Ha! No, we can't. They don't show that. That's right. What a pain in the neck. Okay? Or some other part of the anatomy. Okay. Let's clear the screen here. All right. So what we're going to have, it says from the total resistance of the circuit shown in this figure. Now, here is your voltage supply, electric energy source, and we're going to call this a battery, long line, short line, long line, short line. Oh, no, sorry, wait. Okay. All right. Because they have plus on the bottom, that's the long line there. So this is upside down from what they've got, but it really doesn't matter. And this time we're going to have 3 resistors. Here's one, R1. Here's the second one, R2. And here's the third one, R3. And we're not going to have the light bulb, okay? R3, okay? And they tell you what these are. R1 is 7.00 ohms. R2 is 9.00 ohms. Okay. And R3 is 21.0 ohms. Big old resistor there. Okay. Find the total resistance in the system. Guess what, team? In a series circuit, the resistances add. Okay? You just add them up. Not hard at all. 21 plus 9 would be 30, plus 7 would be our total 37. Oops, wait. 37.0 ohms. That was pretty straightforward, right? Make sense? Now, if they ask for current, well, they can't ask for current because they didn't tell you what the battery was worth. Yeah, so all they asked for was resistance. You just add them up. Just add them up. Enjoy it while you got it. Okay? Now, we're going to do something a little bit different here. In example 2, nothing's the same, so this time you got the 3 resistors there, but then they also show one more resistor down here, R4, and this is going to be 96.0 ohms. Okay, still in series. This R1 is 5.00 ohms. R2 is 13.0 ohms. And R3 is 12.0 ohms. I can't write. Okay, R3. Okay, this time they gave you a battery, the EMF, or E, is equal to 90.0 volts, which is a huge, huge direct current battery. You don't find many of those. Your car battery, 12. A tractor battery might be 24 volts. A bulldozer battery might be 36 volts. Hey, 90? That's 3 times the size of that. I don't even know what you would use a battery like that big for. But anyway, you got it. The question now is, what is your current? This is what you don't know. What are you going to have to do to find out what your current is? You tell me. Anybody? Help me, help me. What formula will you use? What kind of information do you need? How is voltage, current, and resistance related? How is current, voltage, and resistance related? They're third cousins twice removed. No. What were we studying this section? Studying being the operative word. I think it was 17.6, wasn't it? Yes, 17.6. Second? Ohm's law. Okay. There's his symbol right there. Ohm. What was Ohm's law? Page 465. Hey, you got it. That's exactly the one we need. There's three forms of it. That's the one we need if I could write it. It's supposed to be an R and it looks like a B. Okay. We know the voltage. They called it E. I don't know why they called it E, but it's V. That's 990.0 volts. Divided by, what's your resistance of that circuit? Say again? What's the resistance of that circuit? It's a series circuit. So guess what? Just like the last problem or example. What do? Add them together. Here's 96 plus 5 would be 101 plus 25 would be 126, right? So it'd be 126 ohms. Okay? So pull out your handy dandy calculator and see what kind of current you get. Now we'll go into that. 3. So 10 over 34. About 0.3, 0.31, 32, something like that. Anyone got it? 0.71. Is that right? 90 divided by 126? Oh, wait, yeah. I'm sorry. That's a 14. I wrote it down wrong. Yeah, 10 divided by 14. Yeah. Say that again now. 0.714 amps. That seems reasonable. Yeah. Much more reasonable. And let's see what they got. Where did they do it? Okay, I see all the stuff here, but where's the solution? Oh, wait. I'm looking at the wrong problem. 0.714, that's exactly what they get. I was looking at example 3. Okay? So, let's clear that one out. And now let's do example 3, the one I was just looking at. Okay, this time we have a current that we know. I is equal to, I probably shouldn't write it there because that's where I'm going to write a resistor. Let me draw my circuit and then I'll decide what to do. Okay. We'll put a resistor here. This thing can be such a pain in the neck. Okay, there we go. We'll put a resistor here. That's R1 is equal to 23 13.0 ohms. R2 over here is equal to 14.0 ohms. Your E here is 115 volts. I don't know why they don't use V. They use it in Ohm's law, but they don't use it here. They use E over R. I don't know why. Okay? And here's your R3 down here, and this is the one we don't know. That's what we're looking for. Okay? Now, I never did write down my current. Let's put it here. I is equal to 3.00 amps. Okay? Find the value of R3 in this circuit to have that kind of current with that kind of voltage. And again, that's a huge amount of voltage, DC voltage, and that's what they've drawn it as, but I don't think that's going to be the case. Okay? So how would you proceed on this one? How would you proceed? What's your basic formula we're going to be using? That's your key. Second?
Is it the I equal E over R?
Okay. Only this time I think I would be R is equal to E over I. Why? Because we know E and I, we don't know all the R's, right? Okay. So this will be 115 volts divided by 3.00 amps, right? And that won't go in an even number of time, but it'll go in some number. Okay. 38.3, I think. 333, right? 38.333, blah, 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 ohms. That's your effective resistance. We know two of those resistors, right? That's 23 and 14. Add those two together, and what do you get? 37. So that means this one down here must be a mere 1.33, 1 1/3 ohms. 1.33 ohms. Now, why did they round that to 2 digits? Oh, I know. Because in subtraction, that's what you do. Okay? So 1.3 ohms, approximately. You see that? All right, good deal. Let's move to example 4. Find the voltage drop across R3 in example 3. Now, how do you do that? Find the voltage drop across that resistor. Well, what is voltage? By Ohm's law. Say again? I times R. I or what? No, never mind. Okay. All right. And we already know I, that was 3.00 amps. And we just determined that resistor R3 was 1.3 ohms. Multiply that and you get 3.9. 3.9 volts. Very little voltage drop across that one because it's very low resistance. Bigger voltage drops across the other two, The biggest one across R1, next biggest across R2, just a small voltage drop across R3. All right, good deal. Any questions on that? So problem set 17.7, you can do any of the odds 1 through 11. No, 1 through 13. Okay. Now, that was your series circuit. Those are characteristics of series circuit. The same current goes through every resistor in a series circuit. Okay? The resistors add. Just simply add. The voltages drop across each resistor, and that has equal the total voltage drop across the battery. So they're using E across the battery and V across each resistor. Okay? Now we look at parallel circuits. Okay? This is the figure you have in your book, 17.38. And this time we're awfully close to being exactly the same on both of these. Okay? The same colors and everything. I'm so proud of them. They finally got something right. Now, these two circuits are absolutely, completely identical. They don't look like it, but they are. And here's the key with a parallel circuit, if I can get up. Okay. All right. You have your voltage drop across here. Usually you know what your battery is, what rating of the battery is. That voltage drop is the same across resistor 1, across resistor 2, and across resistor 3, because all these are connected directly to the battery. That wasn't the case in a series circuit. There your voltages added up. The drop across one, the drop across another drop. That one with a very low resistance had a very low voltage drop across it. Okay? This one, they're all three the same. So if you know this voltage drop, you know it for all three. You know the resistance of all three. Well, if you know the voltage across this resistor and you know the resistor, divide R into V and you get the current. So there's one current that goes through here, another current that goes through there, another current that goes through there. The total current in this system, you add those three currents up. Does that make sense? So that means your total, because the currents are adding, that means your effective resistance of this block here, whether you do this one or this one, is actually less than any one of the resistors on there. So you put more resistors on there, your effective resistance is going down, not going up. Series circuit, you add more, you add up the resistances. Here you don't. I think we talked about this briefly last time. No, maybe that was my other class. They're doing electricity and magnetism also. So here are the key features here. Let me just see if they're going to do these. No. Goodness gracious, what a weird thing. Here are the key features. The current, the total current in the system is I1, I2, I3. You add the currents. I1 plus I2, I2 plus I3. Okay? Your voltages, as we said, is the same across all of them. V is equal to V1, equal to V2, equal to V3. Those are the same. All three of those are the same. And that's your total voltage across the battery. You could call that E if you wanted to. Now, that makes for some interesting situation, and it's a rather bizarre thing, but because R is equal to V over I, you could do, and all those voltages are the same. Well, get a little hairy doing it. I'll just give you the formula like they did in the book. They didn't explain it there either. 1 over R, this is a total resistance or effective resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now that's rather bizarre, okay? In that you'll find out as you add more resistances, you drop the overall resistors. It doesn't sound like it makes sense, but it does, okay? Now, they go back and do it for a 2 resistor case and show you how that comes about. But they don't show you that on the slide. Where they go on the slide next is this thing about if you're pumping water through 3 different pipes, but they're in parallel with each other. It's sort of the same type deal as what we just said. The total water being pumped through the pump is your I here, and it's the same I here. You're not losing any water. There's no leaks here. And part of this water goes through this pipe, part goes through this pipe, and part goes through that pipe. The pump is providing some pressure, and that pressure is the same across each of those smaller pipes. And each of the pipes has its own resistance. So this is very similar to the case we see here. The voltage is the same across each of these. That's what we showed before. And the currents add, the total current coming through here, I, is I1 plus I2 plus I3. That all add to be that I, but your resistors, and this is the weird part, is related by that reciprocal relationship, which is rather strange, okay? But it is indeed true. So let's do example 1. There are the things I just wrote down, and they summarize that at the end. So let's go back to a page with very little writing on it, and we will erase all that I wrote, and let's do example 1. Find the equivalent resistance of the circuit shown here. R1 is 7.00 ohms. R2 is 9.00 ohms. And R3 is 12.0 ohms. Okay? Without knowing what the current or the voltage is, we just know those resistors. We're looking for what they call the equivalent resistance, sometimes called effective resistance, and that's 1 over R. R is the effective resistance, but the formula reads like this, is equal to 1 over 7. I'm going to leave off the zeros. Remember, at the end, we're going to put 3 significant digits there, plus 1 over 9, plus 1 over 12. Now that makes for a pretty hairy problem, because dealing with fractions here, your least common denominators, I really hate that 7 in there, but that makes it, the least common denominator between 12 and 9 is 36, right? Right? Okay? Nothing smaller will work, 36, okay? But between 7 and 36, you have to multiply. So 36 times 7 is 42, 21, 252. There's your common denominator. Yuck. 252 plus 252 plus 252. Okay? Well, 7 will go into 252 36 times, right? 9 will go into 252. 4 times 7 is 28 times. And 12 will go into 252. Second?
21.
One more time. 21. Okay, 21 times. Because it's 3 times 7, 21. Okay? Add those numerators up, and you get 64 and 21 is 85 over 252. Okay? Now, take that number and reciprocate it. So this is 1 over R, your effective resistance. Flip them, and you get R is equal to 252 over 85. And see what that turns out being. All right, good deal. Thank you. Say again? A little less than 3, right? 2.96. Okay. Ohms. Look at that, folks. You have 3 resistors, 7, 9, and 12. Their effective resistance is less than 3. Okay? That doesn't seem like it makes sense, but it is. That's what happens in parallel circuits. Your effective resistance goes down. It will always be less than the least of these. The least of these is 7. That's considerably less than 7. Okay? Every time. All right, in parallel circuits. And they got 2.96 also. Good for them. Okay? Now, they show you a shortcut sort of to do on your calculator. You can do 7 and hit the reciprocal key, which is the 1 over x key or x to the minus 1 key. Plus 9, 1 over x key or x to the minus 1 key. Plus 12, 1 over x or 1 is equal to, and whatever you get there, hit that key again and that reciprocates it again. You should get 2.96 with some more digits after it. All right?
7 times 1 over.
What's that?
7 times 1 over 8.
Yeah. Do you have a 1 over x key? Okay. 7. It's not times. 7, 1 over x. Yeah. Not times. Yeah. That's the operator key. 7, then press the 1 over x key, plus 9, 1 over x key, plus 12, 1 over x key, equal, and then press the 1 over x key one more time, and you get their effective resistance. You got it? Good deal. Okay, example 2. Find the total current in the circuit shown in 1743, which I haven't erased, thank goodness. Okay? Well, the problem is they didn't give us a voltage, did they? Ah, there they did. They say 17.44. Oh, different problem. Different problem. Okay, this time we'll be over here. Let's use this one. They give you voltage to be 90 volts. That's what they call in the E. Okay, the battery. R1 up here is 23.0 ohms. Okay, R2 is 14.0 ohms. And R3 is 5 ohms. Okay, and it says find the total current in that figure, not the one we just did. I misread that. Okay? How would you proceed to get that? Yes, you first do your effective resistance. 1 over R is equal to 1 over 23.0 ohms. I'm going to leave off all those. Plus 1 over 14 plus 1 over 5. Okay? Again, you can use your reciprocal or 1 over x key, whichever you have on your computer, and do 23, 1 over x plus 14, 1 over x, and this one you could just write plus 0.2 because you know what that is, but you could write, go on and do that, and do equal, and do 1 over x one more time, and what is your resistor? 3.175, blah, blah, blah. Okay? That's your effective resistance, equivalent resistance. Okay? Notice it's less than each one of our other resistors, even less than the 5. Okay? Now, we know the voltage, so we know, since you know voltage and resistance, your current is equal to what? Ohm's law? E over R. Perfect. That'll be 90.0 volts divided by 3.175 ohms. And that's going to be something less than 30, probably around 25 526.
Oh, they rounded it to 3.18.
18. Well, I would leave as many digits as I can on there, and then round at the end. But what do you get? 28.3. 28.3. What units? Amps. Amperes. Okay. 28.3 amps. Wow, a lot of current, because you have a high voltage and lots of resistors there. Effective resistance very low, so you're going to be pumping a lot of current through there. And that is a lot of current. That wire is going to be getting hot, especially here near the battery. The lesser current in each of the others. Those three add going in. Okay. Example 3. Find the current through R2 in this same figure. Okay, example 2. Well, we didn't need to do the previous problem. Who cares? We can do it right from what we know. The voltage across R2 is exactly your 90 volts. Okay? Resistance is that. So I is equal to E over R. So that would be 90 volts divided by 14 ohms. And that would be something a little greater than 6, right? What you get it to be? 6.43? What's that? Yeah. Well, I'm just reading from the book. They may not have rounded right. If they're anything like their test bank, they probably are wrong, but I'm hoping they're okay. I'm so disappointed with that test bank. Man. All right. Let's see if we can get example 4 done. Okay, I'm going to erase all we got. Is that okay? You all right with me erasing? It's pretty exciting stuff, isn't it? Okay. This looks a lot like this first drawing here. We got the E here is equal to 115 volts. Your first resistor is 38.0 ohms. Your second resistor here is 49.0 ohms. And your third resistor, we don't know. Okay, that's probably what we're looking for. And we're told up here that the I is equal to 7.00 amps. Okay? It says okay. It says find the equivalent resistance, okay, and the value R3 in the circuit shown. How are you going to get equivalent resistance if you don't know what R3 is? Hint? Ohm's law. Just plug it in. Ohm's law says the equivalent resistance is equal to E over I. That almost sounds like a really poor joke. I'll wait till the end and tell you the joke. Okay? All right. Give you something to look forward to, right? What is your E? 115 volts divided by 7.00 amps. And that looks like that's going to be something on the order of 116 point something. What they get? 16.4. And that would be ohms. Okay. Now I can guarantee you something. The effective resistance 16.4 obviously is less than R1, obviously is less than R2. It's also got to be less than R3. R3 is going to be something greater than 16.4. I'm just going to guess right now around 20, but that's just a wild guess. Okay? So how do we get it? Do we have to go through those 1 over R's? No. Because guess what? Look at this. Okay? Well, let's see. I say we don't. Oh, yeah, you might. I'm afraid you do. We know the total current, but we don't know each of the currents in the legs. But I still think that would be an easier way to do it than to do the 1 over R's. Okay? They're saying do that. I would, okay, I'm going to show you an alternative way. You might not find this as helpful, but let's do it. First calculate I1, okay? I1 is 115 volts over 7.00 amps, right? That's easy to calculate, right? Okay. I2 is equal to 115 over 49.0. I'm sorry. Whoa. You let me get away with that. You agreed with me. What were you doing? Okay. Don't agree with me when I'm wrong. 38.0 ohms. That's your I1. And this is 49.0 ohms. This is volts over ohms. And then what we do is subtract those two from your 16.4, and that gives you current, and then you know the voltage, and you can calculate resistance. Right? Do those quickly. 115 divided by 38. 3.02 amps. Do this one. 115 divided by 49. Even less. 2 point what? 34? Huh? 3.34, 2.34 amps. Okay. Let's add those two together. You get 5.36 amps. Let's subtract that here, 5.36 amps. And that's going to be right at 11 amps, 11.04 amps. Okay? And then take that and divide that by, your R3 is going to be V over I3. So that'll be 115 volts. See, that never changes in a parallel circuit. And that's divided by 11.04 amps. Wait a minute. I'm sorry. Wait a minute. Whoa. No. I just subtracted amps from ohms and got amps. That's not what we want, okay? Sorry about that. No. I subtracted the wrong thing. Let's pretend we never saw that, okay? Ever, okay? All right. You add these two together, and you get you subtract that from 7 amps, 5.36 amps from that, and you get 1.64 amps, right? That makes sense, okay? And then multiply that by, well, let's see, R3 will then be your voltage, 115 volts, divided by 1.64 amps. What does that give you? Second? 70.12 ohms. Okay. Sorry, I said it poorly before. Let's round that to 70.1. I was thinking backwards on it. They said 70.2, we got 70.1. Okay? Ohms. Okay? And that is what they got. Now, they did it the other way, and if you like doing it that way, it's perfectly fine. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. But the R3 is the thing we're looking for, and after you found out the effective resistance here, you do 1 over R3 is equal to 1 over R minus 1 over R1 minus 1 over R2. That's a lot of keys to hit, but, you know, maybe about the same as what we did. Either way you want to do it. Okay. Good deal. All right, you want well, let's hit this one last slide. There's what we said at the very beginning. The current, the total current in a parallel circuit adds each of the legs together, the currents of each leg. Resistance is your reciprocal relationship. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, as many as you got. But the voltage is the same throughout in a strictly parallel circuit. Okay. Now, I don't think you need to know compound circuits. Let me see. I'm pretty sure you don't, but let me go back and check. Oh, yep, I marked compound circuit, 17.9. Well, we'll do that next time. They'll be fairly quick, hopefully. Now, you want the dumb story? Okay, I need a feel from you. Who's the how many Auburn fans? How many Alabama fans? Alabama. Okay, give me a star player for Alabama. Anyone? Say again? Say again? Jalen Hurts? Okay. How about Auburn? Anyone? Say again? Just name an Auburn player. Who is the big run? Huh? Who's the big run? Huh? Oh, Cam Newton. Let's just imagine they started at the same year. They certainly are not. Okay? They were there taking their college, the special college ACT for football players. You didn't know they had a special one, did they? Yeah. Okay? They were in there taking it, and each one of them were at the desk, doing that. And who you want to speak, Cam or Jalen? I don't care which. Who do you want to be the one asking the question? Huh? Cam. Okay, Cam. Jalen. Shh, be quiet. They're going to get us for cheating, and they're going to kick us both out. No. You walked out of the room. He said, what you want? He said, what's the answer for number 3? Well, Jalen couldn't count too well. He said, what is number 3? And he said, Old MacDonald had a blank. He said, Cam, I can't believe you don't know that. Everybody knows that. I can't believe how stupid you are. Everybody knows that. He said, I know it. It's just the test. I get all panicky. I just want blank on it. What is it? He said, okay, it's farm. Oh, I knew that. Jalen, what is it now? How do you spell farm? Cam, I can't believe how stupid you are. Everybody knows how to spell farm. Well, tell me, I'll just go blank. He said, E-I-E-I-O. Okay. Never mind. And when I had E over I thought of the I-E-I. Okay.
Oh, goodness.
Oh, I recorded that, didn't I? Okay. And Camry will be trying to figure out what we did at the end of the class, okay?